Hello and welcome to this BioProcess International Ask the Expert webcast. I'm your host, Leah Rosen, the online editor for BioProcess International. Before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the question and answer window on your screen. After the presentation, we will begin the question and answer portion, and I will ask our speaker your questions. Your questions in the question and answer window will only be visible to myself and our speaker. So thank you for joining us today. It is now my pleasure to introduce our speaker, Ben Madsen from Thermo Fisher Scientific.
Thanks, Leah. Glad to be here this morning, and good morning to everybody that's able to join the call. I'd like to thank the organizers for setting up the opportunity to present this webinar. We're showcasing some data that we've collected over the last couple of years in our lab, some of these improvements to our HyPerforma single-use bioreactors. And these are really meant for multiple applications, including high-demand applications or niche applications. We've implemented some of these changes based on our interactions with a bunch of customers to support their process needs as they were looking to achieve ideal conditions to cultivate their various cell lines. All the data presented has been generated internally in our lab in Logan, Utah, with internal processes and cell lines and media, but has been shown to be applicable across multiple applications and work done at multiple customer sites. By way of outline, we'll first be discussing where we've been the last few years with our S.U.B design and usage, and where we saw some room for improvement for some of our customers in their most extreme applications. And then we'll go over some of the design changes we made to achieve the demands of those processes with our newest S.U.Bs. And the designs were implemented into our standard products that we're supporting through our field and internal design teams, so they're available to order. And then we'll go over some case studies for the individual applications for each S.U.B and BPC design as shown. And then we'll briefly sum up and show how we envision each of our standard products and how they relate to our recent and upcoming launches of the DynaDrive S.U.B. Our legacy S.U.B design was loosely based on principles used for decades with some modifications to fit the constraints of that are imposed by single-use systems and technologies. And I'm sure most everyone's fairly familiar with the overall dimensions of the bioreactor, these ratios that I've got shown on the slide with impeller designs and ratios, and specifically where our HyPerforma S.U.B design differed was in the placement and the tilted angle of the motor and the drive shaft to achieve radial and axial mixing in a non-baffled bioreactor. And this has been fairly common in a couple of single-use bioreactor designs. And then we've implemented subsurface gassing for both micro and macro spargers to achieve sufficient oxygen transfer and CO2 transfer to support our applications through the past several years. And additionally, we provide subsurface porting within the S.U.B itself so we can get in situ measurement of critical process parameters with single-use sensors or with traditional sensors. The overall acceptance of these first S.U.B designs was really well received in the industry, as evidenced by our high reactor placement across the globe for basically all bioreactor applications. A wide variety of cell lines have been used, from the workhorse CHO clones to more sensitive hyperdomas and adherent viro lines. And additionally, we've seen some usage of the S.U.B in niche applications using primary human cell lines, some insect cells, and even some fermentation applications. When we launched the first 50 and 250 liter bioreactors back in 2006, we knew this would not be the final design, nor the final size offering. And additionally, we saw areas of improvement for both aesthetics and ergonomics and functionality and performance. So over the years, we've seen the addition of increased sizes up to 2,000 liter scale and more pieces within that scale range, and vast improvements in mass transfer for both CO2 and oxygen with the addition of the precision laser drill hole sparger back in 2014. And more recently, we saw the launches of our 5:1 S.U.Bs in 2016 and 2017, which allowed our customers to support lower seed volumes, improve utilization of their facility space by reducing the number of seed vessels and required S.U.B bioprocess containers, as well as the ability to obtain more homogeneous harvest stream through the drain process. And additionally, I don't have it pointed out here, but in 2017, we acquired Finesse Solutions so that we can provide our customers a fully integrated sub and controller combo to streamline the new facility build-outs and to offer better guidance and support of the combined workflow. And continuing with our product improvement last year, we launched our enhanced subs for improved mixing and gassing. And finally, this year and next year, we're launching our newest sub product line called the DynaDrive sub. And this will be the subject of an upcoming webinar in our series. And while I'm sure many on the call would be most interested in hearing about that technology, my focus today is going to be on the enhanced sub specifically, where we implement these design changes to accommodate several applications. As we discussed with several customers, the needs they had for their demanding processes, we noticed similar trends appear. For perfusion customers, they desired higher power input and higher gassing, obviously meeting the porting or having the porting available for their perfusion device. And similarly, for our fed batch customers, they wanted more power input for improved mixing and gassing while maintaining the ability to utilize this lower turn down ratio that we had designed into our 5:1 subs. And then customers working with Adherent cell cultures were keenly aware of the need for better mixing, especially when working with higher concentration microcarrier beads. And while not shearing off the cells from the microcarriers, we'll get into that in a little bit. But because of that, just briefly, the lower mixing speeds are desired in these applications as opposed to the higher mixing speeds. But we still need the higher power input to keep these microcarriers suspended. And additionally, the BPC designs were needed to support media exchanges and trypsin treatments within the bioreactors for these microcarrier applications. So in general, in order to achieve these design improvements, we did simple adjustments for each individual application while utilizing some of our standard parts or some recently developed components that can source and easily implement into the bioreactor design. All subs use what we refer to as an upsize impeller. Essentially, we use the next size up impeller for each sub. So for example, using the 500-liter sub impeller in a 250-liter sub. And then all subs also use the standard 5:1 motor block, which places the drive shaft at a 16.5-degree angle relative to the tank. And this pulls the impeller essentially away from the side of the wall at 2:1 or 4:1 position to avoid any impacting that may occur if we didn't design it this way. And this allows for more optimal mixing in each application as well. And for gas transfer, we designed a new drill hole sparge that we're calling the Enhanced Drill Hole Sparge for the fed batch and the perfusion applications, while our microcarrier applications require legacy designs to support far lower cell density as we see that in the Adherent cultures. And I need to point out at this point that the design improvements we're talking about are suitable for the HyPerforma S.U.B designs built in the last 5 or 6 years. Our oldest legacy subs can't support the motor block and the porting necessary to implement these design changes. We can, however, work with individual customers to work on updating their sub hardware if they desire. In the next few slides, we'll go over each individual design and present case studies of cell cultures that were performed in our Customer Experience Center in Logan. First, we'll focus on the perfusion design and go over a target use case. And first of all, again, I got to point out to begin with, it's important to note that the design improvements we'll be discussing today are specific for our sub sizes from 50 liters to 500-liter scale. This is done for multiple reasons, including staying within our previous safety testing thresholds, as well as supporting what we see as practically used sizes, especially for perfusion due to the logistics of maintaining media and processes at large scales. We haven't seen many requests go beyond about 500 liters. That's not to say that we don't see interest at the large scales, but most of our queries come from up to 500-liter scale. So for our perfusion and in our enhanced subs for perfusion and fed batch, we focused on the 50 to 500-liter scale. One place that we saw immediate improvement in our sub design was by using our upsized impeller method. By increasing our impeller size, we can improve total mixing power up to about and beyond 100 watts per cubic meter in all of our sub sizes. Despite these higher mixing powers, we can still easily stay within the design space of our worst case 1,000 and 2,000 liter SUMs, which utilize similar motors and drive shaft dimensions, which ensures success and safety. We had a customer pursuing higher mass transfer KLA in their 500 liter sub, and so we helped them customize their BPC with an additional microsparger in the back window of the sub hardware, while also utilizing a drill hole sparge and mixing at maximum agitation. Just on a personal note, we knew that this wasn't probably going to be the best solution, but it's the solution that we worked with on this customer to support their needs. And despite their extreme gassing, their extreme gas flow rates, well beyond what we would normally recommend, they were unable to achieve their targets. So we replicated this testing in our lab and showed that we only achieved a maximum KLA of about 42 inverse hours, which is what they were performing in their lab. We showed not only that, but we also showed that despite the extreme gas flow rates that they're using, they're only achieving about 10% boost above what we could already achieve with the standard gassing recommendations that we would give them. So the question became, how can we improve mass transfer while also hopefully reducing the total gas flow rate and exhaust load? Our legacy sub design, when using only the drill hole sparge at maximum recommended mixing speeds and gassing, yields a KLA of only about 10 per hour or 10 inverse hours across our sub sizes, this 550 to 500 liters. And I need to point out again that this has been shown to be sufficient for most fed batch processes through the years when utilizing proper gassing strategies. However, when we improve both the mixing and the gassing in our enhanced subs, we see dramatic improvements in oxygen mass transfer up to about 3 to 4 times using only the drill hole sparger. This increase in gas mass transfer is due not only to an increase in mixing capabilities, but the enhanced DHS. This new DHS has smaller pores, which leads to smaller bubbles being formed during sparging, which ultimately leads to a higher bubble mass transfer area, which improves your KLA. And similarly for CO2 mass transfer, we see we see scalable and high-performing CO2 stripping while maintaining a CO2 to O2 mass transfer ratio of about 0.3 to 0.5, which has been shown to be ideal for most mammalian cell culture processes. And while not required in our standard product, we've shown KLAs even higher still when we implement our standard FRID for each sub. To highlight specifically the design improvements, I'll walk through one of our standard BPC designs. We implemented the new enhanced DHS and upsized impeller to achieve the higher order mass transfer. And for perfusion specific applications, we've added porting for either ATF or TFF devices, as well as a cell bleed port, which is important in maintaining cell density and culture health. For sensors, we include a foam sensor as standard, while allowing the customer to configure the sub with their own conventional or single-use sensor options. I'll quickly go over a case study we performed in our lab using these design changes. And I apologize up front for the condition of our R&D lab in this photo, but simply point out that the ability of the sub to be used in even gray space areas is valuable, even if you've got brooms and garbage cans sitting around like you can see in this picture. The process here revolved around growing a cell clone, a CHO clone in Opticho medium with necessary growth factors. We did this up to 4 vessel volume per day media exchange while utilizing an Excel ATF6 single-use filter system. Gassing was done through only the DHS, using oxygen as the primary gas to maintain DO set point. Agitation was varied through the cell run to provide higher power input and to investigate steady-state gassing requirements at various levels of agitation. One of the keys that we've discovered in especially perfusion cultures is the need to automate as much as possible to avoid the pitfalls associated with manual control and interactions. Therefore, we focus not only on standard process analytical technology such as DO, pH, and temperature, but we also implemented our foam control through the automated anti-foam dispensing linked to an online foam probe. Cell density control by implementing online cell density measurement using an Futura sensor. And lastly, automated media addition using the sub load cells as feedback control to the medium pump. All this was controlled using the TrueBio G3 Pro controller, so that I could sleep at night knowing my process would be fine when I returned to the lab the next day. Our culture ran for a total of 26 days while achieving steady cell densities of 40, 100, 150, and 200 million viable cells per milliliter, and a median exchange rate shown in the graph. And for a torture test of sorts, near the end of the culture, we disabled the cell bleed and allowed the cells to grow to a final cell density of 260 million viable cells per mil, at which point the ATF filter had fouled completely and the run was terminated. All this was done while maintaining viability above 90%, even at these extreme cell densities and packed cell volumes above to 40%, and gas flow rates and agitation rates that we'll go over in the next couple slides. So this slide highlights the gassing and mixing interactions and their effects on the reactor dissolved CO2. DO was maintained, I need to point out, at a set point of 30% air saturation through the entire run. And we noticed the obvious correlations between cell density to oxygen flow rate, as well as the combined interaction with agitation rate. And additionally, we noticed that the dissolved CO2 in the reactor increased or decreased as the agitation was ramped up or down. Importantly, we noticed that the dissolved CO2 remained steady at constant agitation rate despite increases in cell density and oxygen flow rate. And this again highlights the ideal relationship between O2 and CO2 mass transfer that can occur with a single sparger when implementing proper gassing strategy. Finally, we wanted to investigate the relationship between oxygen demand and mass transfer by looking at some of the first principle correlations that we know about. So taking the standard equation for oxygen uptake rate and oxygen transfer rate, we can insert other equations for KLA into our gassing ratios. I apologize for how this slide turned out. Some editing to do apparently. Specifically, KLA models have been shown to show strong correlation between power input per volume and gas flow rate in muscle volumes per minute. And if we substitute these equations into our standard OTR equation and then set our OUR equal to OTR, we can create an overall equation to predict the cell density we could support at a given agitation and gas flow rate. And when we take the data from this case study and plot it out to measure predicted VCD according to our basic model, we see a strong correlation. This leads us to conclude that we can reliably predict gas and agitation demands for specific cell densities while maintaining desired DO and CO2 set points in the reactor. The next application we'll discuss is high-density fed batch processes and the updates we made to the sub to support higher oxygen demand. The mixing and gassing for this sub design is really similar to the perfusion application with similar impeller size and DHS design. And as a reminder, when we increase the impeller size in each reactor, we can achieve up to 100 watt per cubic meter agitation. And implementing our new enhanced DHS, we've shown large increases in mass transfer. It's important to note that the 4-to-1 position of this impeller design, of the impeller in this design, in other words, the lower physical position of the impeller to support the lower seed volumes and better mixing through drain, actually results in a slightly lower KLA comparable to the perfusion version, which showed KLAs in excess of 40 inverse hours at similar power input and gas flow rates. But we do get that enhancement of the lower mixing ability and the lower seed densities with this design specifically. But I point out that the lower KLA relative to the perfusion isn't necessarily terrible because we're still seeing much higher KLA's ability with this sub design compared to our legacy sub designs you can see in the graph. And I'll walk through the BPC design changes similar to our perfusion BPC. And again, we implement our enhanced DHS and upsized impeller along with similar sensing options with standard foam probe and the configurability of conventional or single-use pH and DO sensors. And additionally, the extended 4-to-1 drive shaft allows seeding at lower volume and better mixing through drain. And a carryover from our 5-to-1 subs, we implement the cross-flow sparge, which assists in mass transfer at lower working volumes. To test these design improvements, we performed cell culture studies in all of our vessels using standard fed batch processes. And here we used a CHO-S clone in Dynamis medium with EFC plus feed. The reactors were seeded at 25% working volume on day 0, and then they were fed to 85% working volume on day 2, and then they continued in a standard fed batch process for an additional 14 days with feeds continuously pumped in as opposed to daily bolus additions from days 5 to 12. And here we used EFC pluses at a 2x concentration for a total of 15% volume feed, and a 45% glucose solution was added as needed to maintain glucose targets. Despite the ability of our reactors to be run up to 100 watt per cubic meter agitation, in order to compare to our standard 5-to-1 subs, we ran these cultures at just 20 watt per cubic meter agitation. Gassing was performed using only the DHS, using primarily O2, N2, and CO2 gases, along with the crossflow sparge operated at recommended gas flow rates. As an example, the typical crossflow sparge rate in the 250-liter sub would be operated about 14 standard liters per minute of air, while the 50-liter sub would be about 5 standard liters per minute of air. For pH control, these studies were controlled more loosely with variable pH control throughout the run in order to maintain our PCO2 set points and concentrations in the physiological ranges. And specifically, the pH was controlled at slowly decreasing pH set points for the first 4 days of the culture down to a set point of 7.0, and then allowed to vary depending on the lactate production and consumption. In all the studies, the pH drifted down to about pH 6.8 at peak lactate production, and then crept back up to about 7.0 as lactate was consumed, and then it was balanced. This helped balance the CO2 production during the process, and it was fairly steady at a set point of 7.2 throughout the rest of the run. Results of the study show comparable growth among all of the subs with similar peak viable cell densities and viability profiles. Additionally, not shown here, the glucose, lactate, ammonia, and protein profiles were really similar. We can also note that the low 4-to-1 turn-down ratio allows us to maintain the benefits of our 5-to-1 subs while not impacting the cell growth or the viability. Where the rubber really hits the road in these studies is the comparison of the required gas flow rates between these and similar cultures performed in our standard 5-to-1 subs. Whereas with the O2 flow rates through the DHS for most of our 5-to-1 cultures, they rose to nearly 0.05 vessel volume per minute. These enhanced subs used only half that flow rate to achieve similar cell densities. So for example, the 250-liter 5-to-1 sub peaked at over 10 standard liters per minute of oxygen, while the enhanced sub used only about 4 liters per minute. So this reduces the overall consumption of the more expensive gases and reduces the load on the exhaust filters, which extends their operational life. And importantly, we show that the ratio of O2 delivery to CO2 stripping is also maintained at approximately 0.3 to 0.5, meaning that CO2 stripping is not crushed by the increase in oxygen mass transfer. Lastly, we'll be discussing the enhancements we made to the sub to support our microcarrier applications. This is obviously a little different from the previous two examples where the suspension cultures are less susceptible to impeller shear than adherent cells, so I'll change gears just a little bit here. So whereas with the suspension cultures, we're interested in increasing mixing to increase mass transfer, here we're more interested in simply keeping the heavier microcarriers in suspension without increasing the shear too much so as to avoid ripping the cells off the microcarrier surfaces. For those familiar with these applications, the characteristic variable often used is the Kolmogorov length. This value is calculated to give an idea of what impeller speed can be used without creating eddies smaller than about half to 2/3 of the diameter of the microcarrier bead. If the Kolmogorov length stays high, we have higher confidence that our cells will remain attached in the process by flowing with the eddies rather than being sheared off them. By implementing our increased impeller size, we effectively increase the overall power input ability of the sub while maintaining or increasing our Kolmogorov length. And similarly, for those that prefer tip speed as the deciding factor and the scale factor, we can increase the overall power input while maintaining a desired tip speed. So to again walk through a BPC design, we implement the larger impeller to increase our mixing capability, and sensing options include the standard foam sensor and configurability of the conventional or single-use pH and DO. And because gas demand is typically lower in these cultures, we use the standard DHS and cross-flow sparge, and alternatively, we can implement even the open pipe sparger in these designs. And then similar to our fed batch variant, we use the extended 4-to-1 dry shaft to assist with the lower seed volumes, but also to allow better mixing of the microcarriers when doing media exchanges. We also include a port for decanting for these media exchanges. To test these enhancements, we performed cell culture in our 50, 250 liter, and 500 liter subs using a Vero clone grown on Cytodex-1 beads in VPSFM medium. And scale was achieved with Easy Flask and Easy Fill cell factory systems using the dissociation, quenching, and washing solutions shown on the slide. Cells were seeded in each, wrong slide. To test these enhancements, we did cell seeding at about 15,000 to 18,500 cells per square centimeter, or about 200,000 cells per mil, and they were grown for about 4 to 5 days in each culture. The cells were seeded from a 5-liter glass vessel, and they were transferred into the sub with new beads, followed by 8 hours of intermittent mixing to achieve cell attachment. And it's important to note that for this step, no dissociation reagent was used, but the cells were enabled to transfer to the new beads through the settling process. Starting on day 2, 50% media exchanges were performed by stopping gassing and agitation temporarily to allow the cells and beads to settle, and then decanting through the included port, and then adding fresh medium, and then re-enabling the process agitation gassing. The controller was set to operate at about 0.34 meter per second tip speed with air and oxygen gassing through the DHS. The results showed similar growth of cells in these reactors through 4 days of culture up to cell densities of about 80,000 cells per square centimeter. And although it's difficult to see in the right image, the cells were confluent on most of the beads by day 4 in all cases. And importantly as well, we note that the microcarriers are also fully intact, meaning the agitation and bead concentration didn't result in any bead or cell damage. I'll reiterate that we used no dissociation reagent when scaling up to these larger reactors. The mostly confluent microcarrier beads from the N-1 stage were transferred directly into the end-stage reactor along with fresh beads, and then followed by the intermittent mixing that I described to achieve the cell bead-to-bead transfer. It's important to know that we can only achieve that this can only occur when we use the proper microcarrier beads that have the collagen layer for improved cell attachment. So to sum up, we've shown improvements in mixing and up to 3 to 4 times improvement in mass transfer for our perfusion and fed batch variants of the enhanced sub. And each sub achieved these goals with slightly different design enhancements specific to each process. Our microcarrier variant implemented similar design improvement to our fed batch sub in order to achieve the lower shear and lower tip speed, but higher power input for higher concentration microcarrier applications. So looking backward, we know that the 5-to-1 sub has been shown to support a plethora of processes in its native form. However, the improvements shown in our enhanced sub simply expand on these capabilities to support niche and high demand applications using similar design adjustments to the BPC and sub hardware. The hardware changes can often be accomplished in the field by our qualified representatives, while our sub BPC design changes can occur with our product design teams. Looking forward, we'll tease you with improvements we're now seeing in the newest DynaDrive sub, with still higher peak mass transfer and incredible turn-down ratios as high as 10-to-1 or 20-to-1 turn-down. We're still in the process of gaining data sets for multiple clones and cell types, but we anticipate between the enhanced and the DynaDrive subs, we'll be able to meet any cell culture needs that our customers have moving forward. Finally, I'd like to thank all the colleagues in Logan that assisted in these design changes and the massive amount of data that we've collected over the last couple of years during development. I'd like to thank again the organizers for the opportunity to speak to you, and thank you for your time.
Great, thanks, Ben. And so before we get started with the Q&A, we do have a set of questions for our audience. So the first question is, which sub-processes are you most interested in improving the performance of? The options are perfusion, fed batch, or adherent cells. You can go ahead and click the selections on your screen. That would be great. And then the second question is, which criterion is the most important for you when developing scale-up tech transfer? And the options are peak gas flow, mass transfer coefficient, KLA, impeller tip speed, or power input. So again, if you can go ahead and answer those questions on the screen, we will get started with the Q&A. And as a reminder, you can just go ahead and enter your questions into the question and answer box, and we will begin that shortly. It looks like we're just waiting for a few more answers. Okay. So the first question, Ben, is I'm currently using a 2-to-1 sub with a frit and DHS for sparging for my fed batch operation. Do you have recommendations on how to change and optimize my gassing strategy when I move to the enhanced sub, which only has DHS?
Yeah, we've got some guidance on that. We've actually had to implement similar processes in our own labs over the last few years. So when we, not to get into too much background here, but when we divested HyClone a number of years ago to GE Healthcare, we inherited new cell lines, new media for our subs, and we had to get to know those clones fairly quickly. And what we found with those clones specifically was that they didn't grow in the presence of the fritted sparger. And so what we had to do is completely change our own processes in our lab to do a DHS only sparge strategy. So the things that we have to keep in mind with that is we end up changing the gassing ratios in our subs. So whereas with the frit, we normally put the higher concentration gases, the pure oxygen, pure nitrogen, pure CO2 through that fritted sparge, we now put those through the DHS. And whereas in older processes, the DHS usually only had air going through it, now we're pumping through our higher concentration gases. And so it generally requires us to switch to a more oxygen pure gas instead of relying on air for these processes. So our KLA won't change, but our effective mass transfer will change as that concentration of oxygen in the DHS bubbles increases. So in order to implement this, we actually have to help the customer on a case-by-case basis to get the correct MFC sizing in their facility, whether they're using a separate controller or whether they're using a legacy Finesse or Thermo Fisher G3 Pro or G3 Lab controller or G3 Lite. We just have to make sure that those MFCs are sized to be able to support those processes. But yes, we've been able to get quite a few customers to be able to switch to this DHS only sparging strategy away from the frit.
Okay, and I'm working with an older generation sub. Can I modify it to take advantage of these aspects of the enhanced sub?
Yeah, I kind of pointed it out earlier in the presentation that the designs that we have for this specific sub, for these enhanced subs, are more for the newer equipment. So the limitations are the age of the equipment. So our oldest stuff that was built back in, say, 2006 or even 2010 won't be able to support these. And it's more due to the porting on the subs and then the ability to swap our motors and work with the VFDs within our e-boxes. So anything older than about 2014 won't be able to support these processes. So the things that we have to look for on our sub in terms of the hardware are the overall aesthetic look. So if you go to, say, the Thermo Fisher website and you see the sub on the main pages there, it's basically got that lip on the top of the reactor, and then it's got porting for the 5-to-1 seating in it. And then it also has a port for the ATF or for any type perfusion. One thing that I didn't point out in the slides is that we've actually gone through and updated a lot of our hardware to accommodate ATFs at all size scales, so that any new hardware that's being ordered that's going to be the HyPerforma style sub will already have these ATF6, ATF10 ports in it for the perfusion application. So it depends on the age of the hardware, and you just have to work with your local representatives to figure out whether we can support that change to enhanced sub.
Okay. We're interested in doing perfusion at lower volumes in our subs. Could I modify a fed batch sub to use for perfusion, or am I locked into the 2-to-1 sub you talked about?
Yeah, this one's good, and this has come up a couple of times in conversations with some customers where we've had them interested in doing perfusion down to even the 5-to-1 or 4-to-1 working volume. The limitation here is really going to be porting in the sub. So we have to leave room for pH, DO, temperature, because those are the critical process parameters that basically everybody needs to monitor for their process. Then so that takes up that space down at the bottom of the hardware and in the BPC. And so if you're wanting to add in your ATF port, which is really just minimally one port for a single ATF, or if you want a backup ATF, now you have to have 2 ports. If you're using TFF, you inherently need 2 ports in the sub, and ideally subsurface for both of those. And then if you've got any other sensors, whether it be cell density sensor or CO2 or Raman, or if you want backup DOPH, then you end up really just with a constraint on the amount of space that you've got in the bottom of the sub. So porting really becomes the concern. So our recommendation really is to work at about the minimum 50% working volume, but it depends on where, again, we put that port for the perfusion device in the hardware and in the BPC. So we work with our customers individually on that, but generally we say 2-to-1 is the minimum working volume that we should, which is again why we chose the 2-to-1 drive shaft to improve our mixing for that ability.
Okay. And we don't have time for any more questions. We just have this one more question that we'll ask. If we didn't get to your question, we'll be giving the questions directly to Ben, and he can follow up with you directly. So the last question is, in regards to scalability, do you see a significant change in power number with the increase in impeller and changes in the BRX location?
Yeah, that's a really good question. We didn't go through and do actual power number measurements with this. We just know that the power number ideally is going to be independent of reactor geometry so long as proper spacing is maintained within the sub. And so we do know that as we implement this larger impeller into the sub, we know that some of those ratios change. And so we would ideally need to go through and reevaluate that. But legacy-wise, our impeller power number, we've stated it to have a power number about 2.1. And we stuck with that number through these tests. But again, we haven't gone through and independently verified that. That's on our docket of things that we'd like to accomplish eventually. So right now we've just stuck with the 2.1 for these, and we just recommend that for scaling moving forward.
Okay, well, thank you, Ben.
Thank you, Leah.
And thanks to our audience for joining us. The recorded version of this webcast will be available for on-demand viewing on our website, and as a registered attendee, you'll receive a follow-up email providing you with a direct link. We look forward to having you join us at future BioProcess International Ask the Expert webcasts. And we also want to note that this is the first webcast in a series of 3 on the topic of single-use bioreactors, so be sure to look out and register for the next 2 in the series. All that information is available on the website, and you can look for the email invites as well in your inbox. So thanks again, and goodbye.